the curl of a vector field is actually in itself a vector field. Now, curl actually measures the tendency of a particle to rotate about the axis pointing in the direction of the curl, where the length of the curl vector is actually a measurement of how quickly the particle moves around the axis. As you recall, the length of a vector is the magnitude. So the length of the curl vector is the magnitude of measuring how quickly the particle actually moves around the axis. So if I can draw a quick picture of this, suppose that this is my curl vector. And like I said, what it's measuring is a tendency for a particle to move about that vector. So if you think of this being, if you think of this as being almost like a surface, which it's not, but this vector would be perpendicular to that surface, but it's this particle, the tendency. I mean, I just said that so you can get the idea of what the three-dimensional picture is supposed to look like, because if you haven't figured out by now, I'm not really good at drawing 3D. What I have here is this point right here. I say this is the point X, Y, Z, and then this is the curl of F of X, Y, Z. Now consider this vector field negative yi plus xj plus k. Now what I want to think about is, suppose I have like a paddle wheel. So I have something that kind of looks like this. And maybe one or two more here, if I can not screw it up too bad. And then a handle coming out of this thing. So if you can kind of picture this as being like a set of paddles sticking out in these directions, if I were to take this and stick it into a current, like into water or something, if the current's moving like this, then it's going to make the paddle obviously go around. So if I take a look at this vector field, when I look at this field, here's z-axis, positive y, positive x over this way. When I look at this field, start to tilt it, I can see what the rotation is going to be like. The flow lines are kind of obvious here, and they're concentric circles, what they are. So if I were to take this paddle that I just designed, or kind of drew, whatever you want to call it, and I would drop it in here such that the handle aligns with the positive z-axis, then the rotation that I'm going to get is going to be counterclockwise. Now if I take the handle on the other hand and I align the handle down here so that the handle is facing in the direction of the negative z-axis, then my paddle is going to turn clockwise. On the other hand, if I take this and I stick my paddle in here such that I'm aligning with the, say, well, anywhere actually in the XY plane, so that the handle is parallel to the XY plane, I'm not going to get any rotation. So let's take a look here at a definition. If F is a vector field defined as pi plus qj plus rk on 3 space, and the partial derivatives of p, q, and r exist, then the curl of the vector field is defined as the partial of r with respect to y minus a partial of q with respect to z, I, plus a partial of p with respect to z, minus a partial of r with respect to x, j, plus a partial of q with respect to x, minus a partial of p with respect to y, k. Now, this is kind of tough to remember. Just simply remembering this, you may look for a pattern. You may be able to see a pattern that you remember it by. But it's actually really much easier if I define this gradient operator, or this operator del. And I'm going to define del as being equal to I times the partial of whatever. This is the partial of respect to x. plus j times the partial with a partial respect to y, plus k the partial respect to z. Now this is an operator. I'm thinking this as a logical operator. Now if f is a function in 3 space, then when I use this operator, or when this operator operates on the scalar function f, we actually get the gradient of f. So I'm going to think of the gradient of f as being equal to I times the partial with respect to x of f plus j partial with respect to y of f plus k the partial with respect to z of f, which obviously that's kind of an odd way to write it, but it makes sense in terms of trying to use this operator on f. We'd actually write this as the partial of f with respect to xi plus the partial of f with respect to yj plus the partial of f with respect to zk, which is the definition of the gradient of f. So if I think of this del as a del operator rather than just a gradient, then I can think of the curl of f symbolically as this del operator cross f. So what happens if I take this operator cross f? What I end up with is just basically, by the definition of the cross product, I'll have, see, I, j, and k. Then I have this del operator. And then I'll have f. And if I'm thinking of f as being written in terms of pi plus qj plus rk. So I can represent the components of f as simply p, q, and r. Now, if I do what I would normally do to find this cross product, what I'm going to get is the partial of r with respect to y minus the partial of q with respect to z I minus the partial of r with respect to x minus the partial of p with respect to z j plus, I'm going to drop down here, the partial of q with respect to x minus the partial of p with respect to y, k. Now you notice this does not quite match the definition of curl, which is right here. The only difference is this middle term. Because see, this middle term is plus and this is a minus. And in terms of curl, all we do to rewrite it in that standard form is simply factor out a negative. When I factor out a negative, I get this term is not touched. Partial of r, partial of y minus q with respect to z, I. And then the double negative gives me a positive. Then I get the partial of p with respect to z minus the partial of r with respect to x, k. I'm sorry, that's supposed to be j. And plus this last term, partial of q with respect to x minus the partial of p with respect to y, k. And that does match the definition that I gave earlier for curl. So the easier way to remember this is just simply as the cross product between this del operator and the components of the vector field F.